Welcome to the Deep Dive. We take important source material and, well, we dive deep to pull out the key insights for you.
That's the plan.
Today, we're tackling a really foundational figure in how we think about science. Karl Popper. Specifically, his major work, The Logic of Scientific Discovery.
It's a classic for a reason. Changed a lot of thinking.
Absolutely. So our mission here is to unpack his core arguments about what actually makes science, well, science. We're using Popper's book as our main guide.
Yeah, and hopefully shedding some light on why his ideas were and still are so influential.
You might find yourself having a few aha moments about how scientific knowledge actually develops. It's maybe not quite what you'd initially assume.
Yeah, Popper really focused on this thing he called the problem of demarcation.
Demarcation.
Yeah, basically, how do you draw a clear line between what counts as empirical science, like physics or biology, and other things like metaphysics or maybe even pseudoscience?
Okay, finding the boundary line. Why was that so important for him?
Well, at the time, there were lots of debates, especially with psychoanalysis and Marxism being discussed alongside theories like Einstein's relativity. Popper felt we needed a logical criterion to sort them out, to know what kind of claims we could actually test scientifically.
So what was his proposed dividing line?
His big idea, the really central one, is falsifiability.
Falsifiability, okay.
He argued that for a theory or a statement to be considered scientific, it must be possible, at least in principle, to prove it false through observation or experiment.
Wait, so not proving it true, but proving it false, that feels backwards somewhere.
It does seem counterintuitive at first,
Yeah.
but think about it. A genuinely scientific theory makes definite predictions about the world. It sticks its neck out, you know?
Okay.
If the theory is wrong, there should be some conceivable observation that would clash with it, that would show it's wrong. If a theory is so vague or flexible that any observation can be made to fit.
It's not really telling you much.
Exactly. It's not really making a specific claim about reality that could be contradicted. For Popper, that lack of potential contradiction means it's not empirical science.
Okay, give me an example. Like, all swans are white.
Perfect. That's falsifiable. How?
You find one black swan.
What? One observation refutes the universal claim. Now, contrast that with something like, unicorns exist, but they are invisible and undetectable.
Right, you can't design an experiment to disprove that. If you don't find one, they could just be really good at hiding or truly undetectable.
Precisely. It's not falsifiable. So under Popper's criterion, the swan statement is scientific, even though it turned out to be false, but the unicorn one isn't.
Got it. But Popper wasn't saying non-falsifiable ideas are useless, was he?
No, not at all. That's a really important point. He was very clear. Falsifiability is a criterion for science, not for meaningfulness or importance.
Boy.
Metaphysical ideas, ethical beliefs, artistic statements, these can be incredibly meaningful. They can even inspire scientific theories, but they aren't science themselves because they aren't empirically falsifiable in the same way.
That's a critical distinction. So he wasn't dismissing philosophy or ethics, just defining the boundaries of empirical science.
Exactly. Now, this whole approach put him in direct opposition to another major school of thought at the time, the logical positivists.
Right. You mentioned them. What was their take?
They had a very different idea about demarcation. They were focused on verification. They generally thought that for a statement to be scientifically meaningful, it had to be reducible to direct sense experience, to basic observations or protocol sentences.
So building up from what we can see, hear, touch.
Yeah, and they relied heavily on the idea of inductive logic, the notion that you can generalize from specific observations to create universal scientific laws. You see lots of white swans, you induce all swans are white.
But Popper rejected that.
Fundamentally, he argued that induction simply doesn't work as a matter of logic.
Why not? It seems intuitive that if you see something happen again and again.
But logically, no matter how many times you've observed something, say, the sun rising, you haven't observed all possible instances, past, present, and future.
Okay.
So you can't logically leap from a finite number of observations to a truly universal statement that claims to hold true always and everywhere. There's always the possibility the next observation will contradict it.
Like the black swan example again.
Exactly. You can observe 1 million white swans, 1 billion even, but that doesn't logically prove that a black one doesn't exist somewhere or won't appear in the future.
So verification of universal laws through observation is impossible.
According to Popper, yes. Absolutely impossible logically. But, and this is the crucial asymmetry he highlighted, falsification is possible.
Okay, say that again, the asymmetry.
While countless positive observations can't prove a universal law true, a single reliable negative observation can prove it false. One black swan falsifies, all swans are white. This logical difference between verification and falsification is absolutely central to his philosophy.
Okay, that makes sense. Verification is impossible, falsification is possible. So science, for Popper, isn't about proving things right.
No, it's about proposing bold ideas, conjectures, and then trying your absolute hardest to shoot them down, to refute them through rigorous testing.
Conjecture and refutation.
That's the cycle. The theories that survive the most demanding tests, the ones we've tried hard to falsify but haven't managed to yet, are the ones we tentatively hold on to.
Tentatively. Not proven.
Never proven true in an absolute sense, just the best we have for now, the ones that have withstood the fire.
Okay. Now, how do we actually do the falsifying? You mentioned basic statements earlier.
Right. Basic statements are the tools we use for testing. They're singular, specific statements about observable events, like this particular pointer on this dial reads 10 at time t.
Very specific observations.
Yes. And a scientific theory, if it's any good, will forbid certain basic statements from being true. It predicts that you won't observe certain things under certain conditions.
So if you do observe one of those forbidden basic statements,
then the theory is falsified. That specific observation acts as a potential falsifier.
But wait, how do we know the basic statement itself is true? Couldn't our observation be wrong? Or couldn't we just decide to ignore observations that don't fit our pet theory?
Excellent question. Popper tackles this as the problem of the empirical basis. He acknowledges that even basic statements aren't absolutely certain. Our observations can be flawed.
So what's the solution?
He argues that accepting a basic statement isn't based on absolute proof, but on a decision or agreement within the scientific community. It's a convention.
A convention. Like we just agree on the rules.
Kind of, yeah. But it's not arbitrary. It's guided by methodological rules designed to make testing as objective and rigorous as possible. We agree on procedures for observation, measurement, replication. We agree provisionally that this observation is reliable enough to test the theory. These accepted basic statements form the foundation for testing, but it's a foundation built on methodological agreement, not on ultimate certainty.
So the scientific community sort of agrees on the ground rules for what counts as a fair test.
That's a good way to put it. And this relates to another view he argued against: conventionalism.
Conventionalism.
The idea that you can always save a theory from being falsified. If an observation contradicts your theory, you just tweak the theory a bit, or add an auxiliary hypothesis, or maybe question the observation itself.
Like constantly patching up a leaky boat instead of building a new one.
Exactly. You can always find ways to make the theory compatible with the evidence if you're determined enough. Popper knew this.
So what was his answer?
His answer was methodological. He said, we should make a decision not to play that game. We should decide, as scientists, not to use these conventionalist stratagems. We should aim for highly testable theories and be prepared to discard them if they fail rigorous tests, rather than immunizing them against falsification.
So it's about a commitment to genuine testing, not just making things fit.
Precisely. A commitment to seeking out refutations.
Okay, going back to induction.
Yeah.
We established why Popper thought it was logically flawed. You can't get universals from particulars. Any of the issues he had with it?
Well, he really hammered home that there's no such thing as a valid inductive inference in logic. That leap just isn't justified. He also noted how even philosophers like Carnap, who initially pushed for verifiability, later had to admit that science needs universal laws.
You can't do science without laws like EFMA or principles of evolution.
Right. But then Carnap and others tried to handle this using probability, suggesting maybe laws aren't certain but highly probable. Popper found this problematic too, especially since some logical frameworks assigned universal laws a probability of 0. How can something with 0 probability be scientifically useful?
Okay, so if not induction, how does scientific knowledge grow, according to Popper?
Through that cycle we mentioned: conjecture and refutation, bold guesses, severe tests. We learn most when our guesses are proven wrong, because that forces us to rethink and come up with better, more accurate conjectures. Progress comes from error elimination.
Which leads us nicely to corroboration. If we can't verify theories, what does corroboration mean? Is it just a substitute word?
It's definitely not verification. Corroboration is Popper's term for how well a theory has stood up to testing so far. It's like a progress report.
How well it's survived the attempts to kill it.
Exactly. It measures the degree to which a theory has been tested, the severity of those tests, and the fact that it hasn't yet been falsified.
So high corroboration means lots of tough tests passed.
Yes. But crucially, Popper insisted this is not the same as saying the theory is more probably true in the inductive sense. He rejects the idea that passing tests increases a theory's logical probability.
Why? That seems intuitive too, if something keeps working.
Because, for him, the logical probability of any universal law remains zero. Corroboration isn't about probability, it's about the theory's past performance under fire. It's an appraisal of how severely tested and how well resisted it is.
So a highly corroborated theory is just the toughest contender left standing, for now.
That's a great way to think about it. And it can only be replaced, ideally, by a new theory that explains everything the old one did, plus makes new testable predictions a theory with even greater empirical content and testability.
Okay. What about simplicity? Scientists often talk about preferring simpler theories, Occam's razor and all that.
Right. The appeal of simplicity is strong. Popper acknowledged this. Even Wittgenstein suggested induction works by assuming the simplest pattern.
But Popper was skeptical.
He was skeptical about having a clear, objective criterion for what counts as simple. Is a straight line simpler than a parabola? Is a circle simpler than an ellipse? Why?
Good question. It often feels intuitive, but maybe isn't easily defined.
Exactly. Attempts to define it mathematically, like minimum curvature, felt a bit artificial to Popper. He did suggest, though, that perhaps the value of simpler theories often lies in them being more easily falsifiable.
Ah, because they make more precise predictions. Less wiggle room.
That's the idea. A simpler theory often forbids more observable states of affairs. It has higher empirical content, making it riskier and easier to test. Think of Kepler starting with circles simple, but ultimately falsified, leading him to ellipses. The simplicity led to a testable, though wrong, hypothesis.
Interesting. So simplicity aids testability, which is key. Finally, probability. This seems like a tricky area for falsification.
It definitely is. Popper engaged a lot with the frequency theory of probability, particularly von Mises's ideas.
Which defines probability based on how often something happens in the long run.
Right. In a potentially infinite sequence, a collective. Think of countless coin flips. Randomness is also key. No predictable patterns within the sequence.
Did Popper just accept this?
He explored it deeply, discussed the issues with defining randomness, the axiom of randomness, and proposed his own refinements for defining objective probability and chance-like sequences. But the main point for his overall philosophy is that probability statements themselves aren't directly falsifiable in the same way deterministic laws are.
How so?
Well, if you have a theory that a fair coin has a 50% probability of landing heads, and you flip it 10 times and get 7 heads, does that falsify the theory?
No, not necessarily. It's unlikely, but possible with a fair coin.
Exactly. A short run doesn't definitively refute a probabilistic hypothesis. Probabilistic statements don't strictly forbid any specific finite sequence of outcomes.
So they seem unfalsifiable by his own criterion.
Not quite. Popper's solution was again methodological. While a single outcome doesn't falsify, we can make a methodological decision to treat probabilistic hypotheses as falsifiable by agreeing on a standard. We decide, for example, that if the observed frequencies deviate significantly and consistently from the predicted probabilities over a long run, we will consider the hypothesis falsified. It's about setting a practical threshold for rejection.
So it becomes falsifiable by convention again, based on statistical significance.
In a sense, yes. We also see probability emerge in physics, where macroscopic regularities can arise from the underlying random behavior of many microscopic particles. Popper suggested that encountering chance in the world is akin to corroborating our probability estimates, just like encountering causal laws is akin to corroborating deterministic predictions.
Okay, wow. We've really covered a lot of ground here, from demarcation using falsifiability
to the critique of induction, the asymmetry between verification and falsification.
the meaning of corroboration as surviving tests, not gaining probability.
The role of simplicity and testability, and his take on probability and methodological rules.
So if you had to boil down the core takeaway from Popper for our listeners,
I'd say it's this. Science advances not by proving theories true, but by ruthlessly trying to prove them false. It's a process of critical elimination, of learning from our mistakes through conjecture and refutation. The knowledge we hold is the set of theories that have best survived this critical process so far.
it's a fundamentally different picture of science than the sort of brick-by-brick accumulation of facts many people imagine.
It really is much more dynamic, much more critical.
So the final thought we want to leave you, the listener, with is this. Does understanding Popper's focus on falsification, on the need for theories to be vulnerable to being proven wrong. Does that change how you look at claims presented as scientific? Does it give you a sharper tool for evaluating them?
It's definitely something to ponder, and if this deep dive has sparked your interest, picking up the logic of scientific discovery itself or exploring commentaries on it is highly recommended.
Absolutely. Thanks for joining us for this deep dive into Popper's thought.